Ever pondered over what makes the Fibonacci sequence so fascinating, or why the sum of infinite terms in a geometric series doesn't always result in an infinite sum? This intriguing question brings us to the world of sequences and series in mathematics. Consider a sequence as an ordered list of numbers, a mathematical concept so simple yet so significant. This list, known as a sequence, is signified by the notation _n or _1, _2, _3. The symbol n signifies the position of the term in the sequence. N is always a positive integer. Each term in this sequence is an individual member or an element of the sequence. By way of example, let's look at the sequence 1, 2, 3, 4, 5. This sequence is represented by the notation where n is the term's position in the sequence. Now consider a slightly more complex sequence: 1, 1/2, 1/3, 1/4, 1/5. This sequence is represented as 1n, where 1n is the term's value based on its position in the sequence. But sequences don't just exist in isolation. Mathematics also deals with the sum of terms of a sequence, a concept known as a series. The series corresponding to a sequence, _n, is represented by the sum of its terms, denoted by the Greek symbol sigma, followed by _n. To illustrate, consider the series sigma n, which is the sum of the sequence 1, 2, 3, 4, 5. This series diverges, or in simpler terms, it converges to infinity. But not all series diverge. Take for instance the series sigma 1, n, which is the sum of the sequence 1, 1, 2, 1, 3, 1, 4, 1, 5. Unlike the previous example, this series converges to a finite value, defying the expectation that the sum of infinite terms should be infinite. Well, it all boils down to the intriguing world of sequences and series, a cornerstone concept in mathematics. The sum of the sequence 1, 1, 2, 1, 3, 1, 4, 1, 5 converges to a finite value. Sequences and series can be of various types, including arithmetic and geometric. These mathematical patterns are found in various aspects of life and science. They are essential for understanding the nature of numbers and their progression. In an arithmetic sequence, a fascinating phenomenon occurs. The difference between each consecutive term remains constant. This consistency makes arithmetic sequences predictable and easy to understand. For example, consider a sequence like 2, 4, 6, 8. The difference between each pair of consecutive terms is always 2. The sum of n series, quite interestingly, can be calculated using a specific formula. This formula, developed centuries ago by mathematicians, saves us the trouble of adding each term individually, thereby simplifying the process significantly. On the other hand, in a geometric sequence, each term is the result of the previous term multiplied by a constant factor. This constant factor, called the common ratio, determines the nature, the sequence. For instance, a sequence like 3, 6, 12, 24 is a geometric sequence with a common ratio of 2. The sum of terms in a geometric series also a unique formula. This formula, much like the one for arithmetic series, helps us calculate the sum of an infinite number of terms effortlessly. Additionally, sequences and series can be convergent or divergent. This property is crucial in determining the behavior of the sequence or series as the number of terms increases. If the sum of the terms of a series approaches a certain limit as the number of terms increases, we say that the series is convergent. Conversely, a series is divergent if the sum of its terms either grows indefinitely or does not approach a specific value as the number of terms increases. In summary, sequences and series form an essential part of mathematics, establishing a base to comprehend patterns and analyze infinite sums. Their study is imperative in different fields, such as calculus, analysis, and statistics. These fields rely on the principles of sequences and series for problem solving, data interpretation, and mathematical modeling. So when you encounter a sequence or series, don't just see a list or sum. Instead, remember that it's mesmerizing mathematical universe filled with patterns, sums, and captivating mathematical behavior.